Welcome everybody. Today's lesson is about geometric sequences. In today's lesson, you'll learn what is a geometric sequence, how to write one as a recursive formula, and how to write one as an explicit formula. But first things first, let's go ahead and define geometric sequence. A geometric sequence is a series of numbers that has a constant multiplier. In other words, each number is multiplied or divided by the same number to get the next. We call that constant multiplier R. In the example shown, 4, 12, 36, 108 has a constant multiplier of 3 because 4 times 3 is 12, 12 times 3 is 36, and 36 times 3 is 108. So my R value here equals 3. Let's look at how we might write a geometric sequence as a recursive formula. In example 1, you can see a recursive formula is given to us. If you'll remember, recursive formulas give you the first term, and then you are asked to find the next terms based on the previous term. So, they've given us the first term, which is 5. Now they say each previous term gets multiplied by 4. So to find the next term, I'll do 5 times 4, which is 20. 20 times 4, which is 80. 80 times 4, which is 320. 320 times 4, which is 1280. And then 1280 times 4 is 5120. There's my first 6 terms of the sequence. And again, I'm just multiplying the same number each time. Now it's your turn. Find the first 5 terms of the sequence shown below in the recursive formula. Your first term should be 1.2, and then each term gets multiplied by 5 after that, so the following terms should be 6, 30, 150, and then 750. Alright, now let's see if we can determine whether or not a series of numbers is in fact a geometric sequence. So, in example number 2, I've got the numbers 12, 48, and 192. The ratio from 48 to 12 is 4, and 192 to 48 is 4. So you can see here my constant multiplier is 4. Now, let's try to write this as a recursive formula. My first term in this sequence is 12. And then to find any other term, I'm going to do 4 times the previous term. And this is for all integers greater than or equal to 2. It's greater than or equal to 2 because we've already found the first term. We're looking for 2 and higher. Now you try. Determine on your own if the numbers 5, 10, and 20 are a geometric sequence, and then write your own recursive formula. You should have found that yes, this is a geometric sequence with a constant multiplier of 2. The recursive formula for this sequence should go as follows. The first term equals 5. All the following terms are multiplied by 2 for all integers greater than or equal to 2. Let's flip to the back and check out some explicit formulas. The beauty of an explicit formula is that you can go directly to a term number rather than having to find all the previous terms. This is especially helpful when trying to find large term numbers like the 20th term or the 50th term or even the 100th term. To find an explicit formula, I can use the general formula shown here. In order to write an explicit formula, I need the first term and the constant ratio or the constant multiplier. So, first things first, let's learn how to use an explicit formula. In example 3, I'm asked to find the first, the fifth, the 10th, the 20th, and the 25th terms of the sequence given by this explicit formula. You can see here that 3 is the first term, and negative 2 rather, is the R value. So the first term here should be equal to 3. Now, to find the fifth term, I'll plug in 5 for n. It'll be negative 2 to the 4th power times 3, which equals 48. The 10th term should be negative 2 to the 9th power times 3, which is negative 1,536. To find the 20th term, I simply plug in 20 for n, and I should get negative 1,572,864. We'll leave the 25th term for a later date. Now you try. On your own, find the 1st, 5th, 20th, and 50th terms given by the explicit formula below. Then check your answer. You should have found that the first term is equal to 200. The fifth term is equal to 0.02. The 20th term is equal to 2 times 10 to the negative 17th power. Our numbers are getting very small now. And the 50th term should be 2 times 10 to the negative 47th power. Now, our numbers keep getting smaller because the constant multiplier is less than 1. Because of that, each term gets progressively smaller and smaller. All right, now it's time to write some of our own formulas. In example 4, we want to write the first 6 terms of the geometric sequence, where the first term is negative 3, and the constant ratio is 2. So each term gets multiplied by negative 2. So my next term should be 6, then negative 12, then 24, negative 48, and 96. Notice how the terms are bouncing back and forth between positive and negative. This is because each time I'm multiplying by a negative number. The recursive formula for this sequence would look something like this. My first term is equal to negative 3. To find any term after that, I need to multiply it by negative 2. And that's for all integers greater than or equal to 2. How about an explicit formula? Now, I mentioned that we need the first term, which is negative 3, and we need our constant multiplier, which is equal to negative 2. Now, to plug this all into the formula, I'll have g sub n, so to find any term, I'll take the first term, negative 3, multiplied by negative 2 to the n minus 1 power. There's our explicit formula for that sequence. Again, all I need is the first term and the constant multiplier, and I can plug that into the general form for an explicit formula. All right, 2 more problems. Let's look at an application. In example 5, we're looking at the pattern when a ball is dropped from a specific height. In this problem, the ball always bounces up to 80% of its previous height after each bounce. This forms a geometric sequence because the constant multiplier here is 0.8, or 80%. So we're asked to find an explicit formula. To do so, we need the first term and the constant multiplier. We said the constant multiplier here is going to be 0.8 because of the 80%. Now the first term is tricky. We're going to be looking at the height of the first bounce. So that's this height here. It was dropped from an initial height of 10 meters. So our first term is going to be 10 times 0.8, which is equal to 8. So our explicit formula should look like this. G sub n equals the initial height 8 times 0.8 to the n minus 1 power. Now, to find the height of the ball after the 7th bounce, I'll plug in 7 for n. So G sub 7 equals 8 times 0.8 to the 6th power. This is equal to 2.097. So after 7 bounces, the ball is at about 2 feet. All right, on your own, try to find an explicit formula and the height of the ball after the 6th bounce. Then check your answer. You should have found that the initial height, again after the first bounce, was 12 times 0.9, which is equal to 10.8, and my constant ratio is 0.9. So my explicit formula should have been G sub n equals 10.8 times 0.9 to the n minus 1. After the 6th bounce, I plug in 6 for n, so G sub 6 should equal 6.37. There you have it. You know everything there is to know about geometric sequences, recursive, and explicit formulas. Tomorrow come into class ready to practice.
Trying to do it right. I've been living a lonely life. I've been sleeping here instead. I've been sleeping.